Now we are ready to discover an important result called the remainder theorem. So let's go. So we're going to let p of x be a polynomial function and let k be a real number so that x minus k is a polynomial of degree 1. And we're going to consider the division problem p of x, this polynomial, divided by x minus k. Now let q of x denote the quotient. The remainder for this type of problem will always be a real number, that is a constant polynomial, and we will denote the remainder r. So we have what I have written here down at the bottom. I can write it p of x divided by x minus k is the quotient, q of x, plus the remainder r over the divisor x minus k. And just to bring this to life a little bit, in the previous video we actually did an example. Okay, the k is the 2 in x minus 2. X minus 2 is the x minus k. The remainder r is 8. So whenever you divide by a linear polynomial like x minus 2, whatever kind of remainder you get will always be a number. You won't get anything more complicated than that. So now we're going to take that result in symbols and we're going to write it in that form again. In the previous video I wrote it out with the actual polynomials involved. Now let's write it out in this abstract way. So p of x divided by x minus k equals the quotient q of x plus the remainder over x minus k. And I'm going to multiply both sides by x minus k. And x minus k cancels on the left. We have to distribute it on the right. So it won't cancel when we multiply times a quotient, but it will cancel with the r over x minus k fraction. So we end up with this equation, p of x equals x minus k times q of x equals r. All right, now, next page. I just recopied that same equation. Now, let's evaluate the polynomial p of x at x equals k, where k is some number, right? So I'm going to plug k in for x in this equation. So on the left-hand side, I just have p of k. I'm replacing x with k. I'll get the same thing if I replace the x's on the right-hand side with k. So instead of x minus k, I'll have k minus k. Instead of q of x, I'll have q of k. And I still have the plus r on the end. Now we can simplify this quite a bit because we have p of k equals, the surprise here is k minus k is 0, okay, times q of k plus r. So p of k equals, well, we don't know what q of k is. Q of k could be just about anything, but 0 times anything is 0. So we have 0 plus r. And so p of k is equal to r. And this result is pretty famous. It's something called the remainder theorem. When a polynomial, p of x, is divided by x minus k, the remainder is equal to p of k. And I even reiterated this on a little yellow card here. I worded it, I rearranged the words a little bit, but this is worth writing down separately and remembering now for the rest of this course. The remainder when p of x is divided by x minus k is equal to p of k. Now what I want to do is let's go ahead and do an example. And actually, whoops, before we do an example, I just want to refer to this example. Let p of x be x cubed minus 15x plus 30. The remainder, when we divided p of x by x minus 2, was equal to 8. And here again, I'm just showing you this division we went through in an earlier video. There's the x minus 2, there's the p of x is the dividend polynomial, and there's the remainder 8. So by the remainder theorem, p of 2 must be equal to 8. Now we never plugged in 2 into this polynomial, but we know if we plug in 2, it has to be equal to 8. And here we can check. Take p of x equals x cubed minus 15x plus 30. P of 2 is 2 cubed minus 15 times 2 plus 30, which is 8 minus 30 plus 30, which is 8. Notice it checks out. So that's not how we got the 8 in the first place. The 8 was just a remainder on long division. And you might say, well, isn't it easier to just plug in? And I'd say here it is. But we're going to see this leads to some really interesting results along the way. So now I want to look at another example. And this is a function we haven't looked at yet. So let p of x be this polynomial, x to the 5th minus 2x to the 4th minus 11x squared plus 5. We're going to use the remainder theorem to find p of 3. Now, all p of 3 means is what you get when you plug 3 into this polynomial. But there's this magical connection between this and division. So I'm going to set up my long division. I have x to the 5th minus 2x to the 4th. I got to write plus 0x cubed minus 11x squared. I have to write plus 0x plus 5. Ugh, what a mess. Now, to use the remainder theorem, I want to divide by x minus 3. And now I'm going to go through the long division process. You don't need to know how to do this. In fact, we're going to have a very short, fast way of doing this in just another video or so. But for this example, I want to go through this a long way. So what times x is x to the 5th? That's going to be x to the 4th. And I want to go kind of quick because, again, you don't have to reproduce these steps. When I subtract, I'm going to get x to the 4th plus 0x cubed. What times x is it? That's going to be x cubed and minus 3x cubed. Subtract. I get 3x cubed minus 11x squared. I bring down. What times x is 3x cubed plus 3x squared. And then I'm going to get minus 9x squared. And I'm going to subtract. That's negative 11 plus 9 is going to be negative 2x squared. Bring down a 0x. This will be minus 2x times x is minus 2x squared. Minus 2x times negative 3 plus 6x. Subtract. I get minus 6x. Bring down the plus 5. And what times x is going to be minus 6 times x is minus 6x. And minus 6 times minus 3 is plus 18. Subtract. I have 5 minus 18 is negative 13. So there's the remainder. So what we just calculated is this remainder. We can say that p of 3 must be equal to negative 13. This is by the remainder theorem. So if I plugged 3 into that original polynomial and simplified, I will get negative 13. Now we're going to see soon that this is actually going to be a great time saver. It doesn't seem so yet, but it will be in maybe even the next video.